Uh, Good afternoon, everyone. I'm Kaushik. I'm a postdoc in IP Bhubaneswar under the mentorship of Professor Saha. So, today my topic of presentation is tailoring first and second order topological superconductivity in heterostructures of P-wave magnets. So, before we go into that, we shall very briefly look into what are topological insulators. Just a recap. So, topological insulators have a defining feature of the bulk-boundary correspondence, that is, the bulk is insulator, but the boundary states are gapless and behave as conductors. So, the topology in this regard is a property of the electronic structure of the system, and they are protected by the bulk, but often due to the symmetries also, they are symmetry protected, and the topology remains unchanged under continuous deformation of the system unless and until the gap is closed. So, the topological states are quite robust under disorders and symmetry preserving perturbations, and from a dimensional perspective, they can be broadly categorized into first, second and third order, as you can see from this schematic with their signature boundary modes. So, we are interested in a particular type of topological insulator, the quantum spin-Hall insulator. So, it was first discovered in the HGT CDT quantum well, which exhibits the band inversion phenomena, which gives rise to such kind of topological insulator behavior. And due to the preservation of time reversal symmetry, the spin momentum locking is observed, which means the one spin goes in one direction, the opposite spin goes in the other direction along the edge, as shown from this bottom schematic. The polymetrices, the topological invariant in this case is given by the Z2 index, which is 0 for trivial and 1 for topological regime, and the transition is regulated by the ratio m/2b. So, if you look into the ribbon geometry, we can see that in the topological regime, the edge modes are helical in nature, which means that each edge has two spin momentum locked dispersive edge states, whereas the trivial modes do not have any such edge states and they are completely gapped out. Similarly, in the sheet geometry also, we can see the topological regime has states inside the bulk gap, and they look in this form, all localized all along the edge. Whereas in the trivial regime, there are no such edge states inside the gap, and they look and at the edges of the bulk gap, the bulk states look something like this. So, the bulk boundary correspondence is clearly visible. So, let us change gear and see what are P-wave magnets that we are interested about. So, they are an unconventional class of magnetism which are odd under parity in momentum space, and they are collinear, non-collinear, coplanar, and exhibit zero net magnetization, as you can see from this schematic shown here. So they differ from the conventional classes of magnetism like ferromagnetism and antiferromagnetism. So they have been experimentally observed very recently in these two materials, and the schematic minimal model is given in this form HPWM, where GSD is the coupling between the itinerant and localized electrons, and alpha is the spin split hopping between nearest neighbor. This preserves the composite time cell symmetry, which is a time reversal plus a half unit cell transformation, and it exhibits broken C4 symmetry. So this part C4 symmetry will be important when we see next. So the question that we try to answer is that what happens to the topology of the spin-Hall insulator when such kind of unconventional magnetism is introduced along with superconductivity. So what we get is topological superconductivity, which is defined by a bulk which has a superconducting gap in the Cauchy-Barrett spectrum, but hosts Majorana zero energy modes inside the bulk. So the BDJ Hamiltonian can be written in this form, where HBHZ is the Hamiltonian for the quantum spin-Hall insulator part, and HPWM for the P-wave magnet, and delta is the proximity induced isotropic S-wave superconducting pairing. So here is the schematic of the heterostructure that we propose. So what we observe from such kind of heterostructure is that both first and second order can be obtained. So if you look into the first order, so discuss the first order. So this Hamilton HBHZ, it has all the three symmetries, and hence it belongs to the BDI class according to the 10-fold classification. So unitary transformation can be obtained such that the Hamiltonian can be unitarily transformed into a antidiagonal form, and a 1D winding number can be calculated. And so we look into panel A, the periodic spectrum shows the bulk is mostly gapped except for 4 isolated points, which translates into minor flat edge modes, as we can see from panel B for the Riemann geometry dispersion. And in the panel C, we can see the shear geometry for the same parameter values, and we can see clearly the edge modes localized along the two opposite edges. Here, due to the broken C4 symmetry, it only occurs along a single direction. And if we want to see, like if we plot the JSD as a value of kxy in the for the winding number, we can see here that for JSD greater than 1, the system becomes topological, as you can see from panel D. For the second order, it is obtained in the regime between 0.5 JSD between 0.5 and 1, as we can see from panel A here. And if we plot the L dots at 0 energy, we can see the Majorana corner modes as seen from panel B. So due to the cardinal symmetry, the quadrupolar winding number can be calculated in this form, and for nxy equal to 0, it is trivial or gapped. For nxy equal to 1, in this case, it is the second order topological phase, as you can see from panel C and D with varying m0 and JSD values. And for nxy equal to greater than 1, it goes to the it indicates the gapless modes. So nxy equal to 1 is what the second order phase is indicated. And if we vary the JSD versus m0 and plot the bulk gap, we can see an indication of the phase transition, as we can see from panel E. So to understand analytically why it happens, why the first and second order phase they appear, we can do an effective low energy theory and expand around the gamma point. We can find two edge Hamiltonians in this form and their respective mass gaps as G1 and G2. Then the Jacobi condition for this case appears in this form, and we can plot in this here in this way. So in the JSD versus delta naught space, if we fix delta naught and vary JSD, we can see that at point A, the system is trivial. There are no edge modes whatsoever inside the bulk gap. For point B, when the Jacobi condition is satisfied, we can see clearly the corner modes, 4 corner modes to be specific. And in point C, when it goes again out of the Jacobi region, we can see the first order phase reappearing. So in conclusion, we propose a heterostructure of the quantum Spielhorn insulator and a PV magnetism with proximity induced isotropic pairing to exhibit both first and second order phases. The presence of chiral symmetry leads to characterization of both first and second order using the 1D winding and quadrupolar winding respectively. The breaking of C4 symmetry but preservation of C2 symmetry is necessary to obtain corner modes in this case. And the effective theory shows that the parameters of the PV magnet, JSD and alpha, can effectively tune the transitions between the different phases. So in the end, I would like to thank Professor Rojit Shah for his mentorship and the group members for the discussions. I would like to thank IIP Bhubaneswar for providing the research facilities and the opportunity. I would like to thank Department of Atomic Energy for the funding. And I would also like to thank the QMAT organizers for providing me the opportunity to present my work here. Thank you.
Maybe on quick question, in your slide number 9, when you talked about the Majorana edge mode.
Yes, sir.
So normally Majorana edge modes, so what is the spin structure in the sense it has both the component contribute because you have you start with quantum spin hull,
yes.
Upspin and downspin, you have both things, you have two linear combination of that. You have also POH superconductor.
Yes.
Normal Majorana edge mode has both the spins same.
Yes, yes.
But here, what is your structure?
Here both, like here time difference symmetry is preserved, so both are contributing equally.
Contributing equally.
Yes, yes.
Any other question? So if not, please thank the speaker.
Thank you. Hello. Yeah, I think it is working. Pointer.
Okay. So myself, Dr. Menpal Singh. I'm currently working at BML Munjal University at School of Engineering and Technology. This is the work I'm presenting today is related to my PhD work, which I did at JNU only with Professor Patnaik. So the motivation behind this work was, as we all know, in cuprates, in pnictides, and even in transition metal dichalcogenides, the superconductivity is accompanied by a certain long range ordering like CDW or like antiferromagnetic insulating phase. The second motivation was TMD has a distinct layered structure, so you can tune them by gate tuning, you can intercalate them, you can mechanically exfoliate them. So there are several ways by which you can tune the properties of TMDs. The third is you can use disorder as an effective probe, because it serves as a powerful tool to investigate the effect in correlated systems. A complex interplay between superconductivity and CDW, as Professor Mahanta earlier said, that usually the CDW competes with the superconducting phase, but in some systems it also like accompanies or helps the superconductivity CDW phase. And the fifth and the most motivation was recent theoretical and experimental reports have claimed that there may exist some metastable phases in presence of disorder, which are indeed stabilized by disorder. So this is the very brief summary of recent work which we published in Physical Review Material last year. We prepared TiACS polycrystalline material by solid state reaction method, but surprisingly we observed a filamentary superconducting phase in this particular material. Earlier report which were there for single crystal as well as the polycrystalline material, which didn't consist only CDW phases but no superconducting phases. So as you can, so pointer is pointer this is okay, thank you. So as you can clearly see a diamagnetic transition and a splitting between ZFC and FC at 7 Kelvin. So the superconducting transition at 7 Kelvin and reduction in TC with increase in external field you can clearly see. So it suggests that the phase we have observed at 7 Kelvin is a superconducting phase. Indeed the volume fraction is very low. So it is not a bulk superconducting phase, but it's a filamentary superconducting phase. But then we suggested that what may be the possible origin behind this superconducting phase. We suggested that the dislocations which were occurred during the synthesis process, those were intragrain dislocation which we observed in the TEM images also. So the intragrain dislocations basically disrupt the periodicity of CDW and incommensurate the CDW phase, and those incommensurate regions basically give rise to a filamentary superconducting phase. So after that we thought why we should not study the effect of matter intercalation in this particular material, how this superconducting filamentary superconducting phase evolves, and in this particular paper we could observe the local moments of titanium local moments in the pristine TiACS compound. So how that copper intercalation or the copper doping affects the local moments. So we prepared a series of materials with the corresponding concentrations of X is equal to 0, 0.06 and so on. So we applied the same synthesis method, the solid state reaction method. As we can clearly see, the space group is 164 trigonal symmetry, which is P3 bar M1, and this is the SAED pattern. It clearly resembles or accompanies the XRD pattern beautifully, and the peak shift toward the lower angle in the XRD hints toward the successful intercalation, and the variation of lattice parameter we have shown in this particular graph. It shows that initially from pristine to 0.06 the lattice parameter enhances in a very linear manner. After that it somehow decreased or becomes nearly constant, which shows the solubility limit of this copper intercalation, that after a particular concentration it basically doesn't intercalate, it finds some interstitial sites or so on. So here are the four room resistivity data for the four samples. This is for the pristine sample. As we all know, in pristine TiSE2 we have observed usually a CDW transition nearly 200 Kelvin. But as we dope the sulfur in the system, it basically incommensurate the CDW. It lowers the CDW temperature nearly 60 to 70 Kelvin, and intensity of the CDW hump is also lower due to incommensuration. But in the copper intercalated system, we can clearly see almost monotonous resistivity behavior up to the room temperature. We could observe a localization behavior here near 35 Kelvin, below which the resistivity goes upwards. In pristine sample, we had ascribed this localization behavior to local moments as well as the weak localization behavior. So to confirm that we have intercalated the copper in the system, and what we observed, you can clearly observe this is the pristine system which has a localization behavior below 35 Kelvin, and as we enhance the copper concentration, the localization disappears and we observe a monotonic metallic behavior in the sample. So we have fitted the resistivity data for all the 4 samples using this formula where rho naught shows a prime root T is localization component, weak localization component in disordered granular materials, and the T square component basically consists 2 main mechanisms. First one is the conventional electron-electron scattering in Fermi liquids, and the magnetic contribution which is coming due to the scattering of electrons due to localized Ti moments. So in pristine sample we could find the localized Ti moments, but as we dope the copper concentration at higher concentration, we can clearly see the main contribution is only coming due to the T square and not localization. Because in localization part we can clearly see in pristine sample the A prime factor leading to the negative value, which gives this rise in the resistivity, and as we go to the higher concentration, the only contribution which is coming is due to the B prime, and that too, although it has 2 contribution, one of them is in magnetic contribution and second one is the Fermi liquid. So in x is equal to 0.11, the only contribution which survives is the Fermi liquid contribution. To confirm whether the copper intercalation or the copper doping has suppressed the local moments, we did this magnetoresistance measurement for the 4 samples. We can clearly see in the pristine sample the magnetoresistance remains negative up to the complete 6 Tesla range, and the parabolic behavior suggests that in pristine sample the mainly this negative magnetoresistance is due to the local moments, although there is a competition between weak localization and the localized moments also, but if it would have been due to weak localization predominantly, there would be a cusp-like behavior, but in pristine the complete parabolic nature suggests that local moments dominate the magnetoresistance. As we increase the copper concentration, we can clearly see the negative magnetoresistance contribution gets suppressed, and at x is equal to 0.11 we only observe a positive magnetoresistance which is due to only Lorentz classical Lorentz factor. Yeah, so we have tried to fit this magnetoresistance data using the Khosla-Fisher model initially, because we had assumed that the only contribution which is there is due to the local moments. So the value of C1, which suggests the magnitude of the local moments, we can clearly see it is getting suppressed as we increase the copper concentration in the samples, and for particularly the sample with x is equal to 0.06, we observed a non-Fermi liquid behavior in the almost a complete temperature range. We have fitted the data using the rho T is equal to rho naught plus kt to the power n, and n is equal to 1.7 fits the resistivity data in almost complete temperature range above the localization temperature. Although we could also fit the same relation for x is equal to 0.09 concentration also, it suggests that here we can conclude the electron-electron and interband electron phonon scatterings are playing the role in this particular temperature range. So these are the conclusion of my work. We report the experimental evidence for filamentary superconducting phase in polycrystalline TiSES, basically which were possibly originated from intragrain dislocations which are caused by strain induced disorder during the synthesis process, and basically what they do, they basically incommensurate the CDW phase, possibly giving rise to a filamentary superconducting state which is metastable in nature and stabilized by disorder itself. The second was we have studied the effect of copper doping, which shows the variation of structural and transport properties. Enhancement in metallic character with suppression of TI local moments is observed, and TI validates basically the existing theories that disorder can drive superconductivity in presence of CDW and in presence of disorder also. So thank you so much. These are the collaborators and so thank you.
So any question you want?
Yeah, so it's a very naive question, but by seeing magnetoresistance graph, you can tell which type of scattering it is. Can you like explain it a little bit, like what, how do you use the magnetoresistance graph
Okay.
to tell which
Okay.
type of scattering?
So usually when you observe only a positive magnetoresistance in a conventional material or conventional metal, the basic origin of the magnetoresistance is the electron. When you apply the magnetic field in perpendicular direction, the electron revolves in the circular path and it gives rise to resistance. That is the conventional magnetoresistance, and it is in parabolic in nature but positive magnetoresistance. So when you have a negative magnetoresistance, the possibility there are which are either you have weak localization. Weak localization comes in when your phase coherence length is longer than your elastic mean free path, right? But this is a granular polycrystalline material, so we are suspicious that the phase coherence length is that longer or not greater than the elastic mean free path. And the second possibility may be a condo or the localized moment scattering, right? There are local moments which basically scatter with your conduction electron, and then it gives rise to a negative magnetoresistance. So in condo like or in localized moment scattering like behavior, you usually observe a parabolic kind of negative magnetoresistance, while in the weak localization case there is a cusp like behavior. So in pristine case we couldn't see any cusp like behavior, so primarily we are ascribing it to maybe a scattering due to localized movement, and that we have also observed in our magnetization data, which I have not shown here. So these are, yeah.
Any other question? So if not, thank the speaker.
Thank you.
Good afternoon, everyone. And I am Atul from Department of Physics, IIT VHU, and I am here going to present my work on superconductivity. The system is NiVi3. So before going to forward, I would like to tell let me introduce some basic introduction about the NiVi3. So NiVi3 is an intermetallic compound. Basically, the intermetallic compounds are which are formed from two or more elements of P and D block, and so due to the low melting point of the elements, these allowed to grow as high quality single crystals. So this system NiVi3 is a controversial system. Okay, so these are the outlines of my talk. Why did I choose this system? Then I grow the crystals and study through the magnetization resistivity, random penetration depth, specific, and the conclusion. So why did I choose this system? So NiVi3, this system is controversial. Some group have published that it is a conventional fully gapped superconductor, and some groups have published that it is a topological superconductor. So I will not go deep about those studies. So I have studied through the magnetization resistivity. So we have grown the high quality single crystal by changing some amount of flux, and the single crystal reflection which shows single peak around 0,0 direction. So this suggests that my system is grown around the C direction, and there is no impurity peak in the system which shows the purity of the crystal. So This is the DC magnetized data in both the direction, in plane and out of plane. Here we are saying that it's a clear transition in both direction at 4 Kelvin, and the bifurcation between zero field cooled and field cooled data suggests that it is a type 2 conventional superconductor. So then we perform the magnetization data under field to calculate the second critical field. So in both direction we performed this experiment and found that the second critical value is around 1 Tesla in plane direction, and out of plane is 0.5 Tesla. So this suggests that the system has a highly anisotropic, and these are the single MS isotherms at different temperatures. So first we calculated the critical field, first critical field. Then from the critical field we calculate the superfluid density and fit it with different theoretical models. Here we are saying that it is nicely fitted with the S wave. So which suggests that it is a fully wrapped BCS superconductor. And then we performed to give to go deep more insight into the superconducting regime. We performed the London penetration depth measurement using a tunnel diode oscillator. So the insight is the full range in full range London penetration depth with varying the transition. Here we are saying that it has clear transition around 4 Kelvin, and then we fitted it with different theoretical models to check this system has any nodes or nodal lines. But here we are saying that penetration depth is when we fitted with the linear model, so it is deviating from the experimental data. Also in the case of T square, but it's nicely fitted with the BCS case. So again, it suggests that is a fully gapped BCS superconductor. So this is the superfluid density which we calculated from the London penetration depth. Again, we fitted with different theoretical models, but here we are saying that it is fitted nicely with the S wave. Again, it suggested that it is a conventional superconductor. Then we perform the resistivity data. So we fitted with this called the Belauzgurin-Silmont formula, and we found a device temperature value around 100 Kelvin, and we performed also the in presence of magnetic field to calculate the critical field. So we found that the critical field around 0.5 Tesla. So this is the specific heat data under various magnetic field down to 100 millikelvin. So we analyze this system in the pure electronic range, which is called TCY3, and fitted it linearly with Cp is equal to gamma t plus beta cube to find out the Sommerfeld coefficient gamma. And what we found that the gamma varies linearly with the field. So again, it's a fingerprint of the fully gapped superconductivity. And we also checked there is a extent of nodal points or nodal, but we didn't find those. So then we calculated the electronic part of the specific heat and fitted this called the electronic specific heat formula. So this is the fitting. We fitted with the S wave. So it is nicely fitted with that to check any existence of anisotropy. We also checked with the D wave. But in the electronic range TCY3, it is completely deviating from the experimental data. Again, it's suggesting that it is a conventional VCA type superconductor. So this is the conclusion. All of my result shows that it is a conventional BCS fully gapped superconductor. I didn't find any nodes, nodal points, and so the symmetry is S wave, which suggests that it is a fully gapped BCS superconductor. So this is my research group. My boss is sitting there, and Professor Patnaik, Professor Lin, my friend Kunal. Thank you.
Any questions?
you mentioned it is superconducting current is different in different direction.
Yes. Yes, sir.
Any other question? So if not, please thank the speaker.